Welcome. This is Miss Wiesen, and right now you are listening to the fourth podcast in Unit 3. We've spent some time talking about gases and gas laws, and this podcast is going to kind of conclude all of that by talking about the density of gases and something called Dalton's law of partial pressures. Okay, so right now we're at the top of page 15, and I'm going to introduce something called molar mass kitty cat. I know it sounds stupid and it's corny, but really it's going to help you. You can see that's one of the reasons why I put a picture of Garfield. But anyway, so think about this. Don't all good kitty cats use their litter box? You're thinking, yeah, what's going on here? And of course they do. They do this by putting dirt over their pee. So check it out. If you're trying to calculate the molar mass of a gas, you're going to use molar mass kitty cat. And here's why. So the molar mass is equal to dRT over P. All right, so let me just show you. The two M's could be the kitty cat's like paws, right? There's other little front paws. And then you can have the little kitty cat. There's his whiskers. All right, so here's how you'll remember this equation because they do not give it to you on your AP reference sheet. Now, you're only going to use molar mass kitty cat when you're trying to calculate the density of gases that are not at STP, okay, that are not at standard temperature pressure. And if you look at the equation, what does the cat do? Good cats put dirt over their pee. Do you see what I'm talking about here? Now, I know it's cheesy, but you will remember this. So, density of gases, all good kitty cats, molar mass, put dirt over their pee. All right, and you can see in this equation, lowercase d is density, r is our R constant, T is temperature, convert to Kelvin, please, and P will be pressure in atmospheres. So, let's go ahead and do exercise 24 so you can kind of see how to put this molar mass kitty cat into effect. Remember, you're only using this particular formula if conditions are not at standard temperature pressure. So let's take a look at exercise 24, and you should quickly see that conditions are not at STP. And that is because we have a density of a gas. It's measured at 1.5 atmospheres at 27 degrees Celsius and is found to be 1.95 grams per liter. That's the density of the gas. One more thing I forgot to tell you back up here, you guys. Notice that the density of gases is measured in grams per liter, okay? This is not grams per mil, okay? So make a clear distinction here that when you're trying to do the density, when you're talking about density of gases, the unit is grams per liter and not grams per mil. And so let's go back down here. We have the density of that gas is 1.95 grams per liter, and it's asking us to calculate the molar mass of the gas. And clearly we are not at standard pressure temperature, so we need to use molar mass kitty. And let's write our givens. Sometimes that kind of helps just pulling these things out from the problem. Okay, so check it out. I just went and pulled all my givens out from the question. Go ahead and convert your temperature to Celsius to Kelvin. And I will write the equation one more time so you can continue to see it and familiarize yourself. Molar mass of a gas is equal to density times the R constant times the temperature divided by pressure. Okay, now we plug and chug. There's all of our values plugged in. Let's cross cancel units. Okay, what do you have remaining? Take a look real quick. You should have grams. Oops. You should have grams and moles remaining as your unit. And actually, when we do molar mass, it's grams per mole. So hopefully that makes sense. Pull out your calculator. Go ahead and do this calculation. I did put the answer down here, but you should always double check with your calculator and your calculations that you're doing everything correctly. And you should get 32 grams per mole. It looks like if we needed to round to 2 sig figs, because if you look over in the problem, this one has 3 sig figs, our temperature only has 2, and our density has 3. And our R constant we won't typically use as a reference point for sig figs because it is a constant. Anyway, if we rounded to 2 sig figs, it would be 32 grams per mole. So right now we're going to get into a big concept on gas mixtures and partial pressure. One of the things that we always refer to this as is Dalton's law of partial pressures. You are going to find that your AP reference sheet gives you these formulas. So if I were you right now, stop and pull out your AP formula sheet to see where these are, okay? Now, AP loves this concept. It's a concept that incorporates mole fraction and pressure, and it's used a lot. So this is going to crop up on the AP test, probably especially in the multiple choice area. I am really just trying to give you guys some information so you can increase those scores. Now, what is gas mixtures and partial pressures? So the pressure of a mixture of gases is the sum of the pressures of the different components of that mixture. So take a look here at the image in your notes. An example would be air. Air is a mixture of gases, as you can see here. So one of the easiest gas laws is to get the total pressure of a system, you are simply going to add the pressures of each individual component within that mixture. So that is total pressure is equal to the sum of its parts. Remember, these gases aren't necessarily reacting, they're just hanging out. Again, this is given to you on your AP reference sheet. In a second, we will do a practice problem involving these concepts. John Dalton's law of partial pressure is also going to use the concept of the mole fraction. Okay, mole fraction is represented by this Greek symbol here, this chi symbol, that is not an X. And so if you are trying to determine the mole fraction of gas A in a mixture, you would simply say, well, it would be whatever the moles of that A gas is divided by the total moles of each gas. So the moles of A plus the moles of B plus the moles of C, so on and so forth. Now, this looks a lot like, I don't know, percent composition, percent error, in the sense that you are taking something you're interested in, dividing it by the total of things in that system, okay? If you're interested in the pressure exerted by gas A, for example, that is due to the mole fraction of A times the total pressure of the whole entire mixture. Okay, now this is not meant to confuse you guys. This is actually pretty basic and simple. We'll do an example here in just a second. But at the end of the day, the partial pressure of each gas in a mixture in a container is going to depend on the number of moles of that gas. And so the total pressure is going to be the sum of the partial pressures, and it's going to depend on the total moles of gas particles present, no matter what they are. Okay, let's do an example. We've got exercise 5. And we are looking at a mixture of helium and oxygen. They're used in scuba tanks to help prevent the bends. For those of you who don't know, if you've never been scuba diving, the bends, if you experience that, could be very painful. For a particular dive, 46 liters of helium at 25 degrees Celsius in 1 atmosphere and 12 liters of oxygen at 25 degrees Celsius in 1 atmosphere were pumped into a tank that had a volume of 5 liters. So it sounds like they're going to definitely compress the gas within that tank, okay? Calculate the partial pressure of each gas and the total pressure in the tank at 25 degrees Celsius. So you're going to think about this in a couple different steps. Again, I encourage you to try to work some of these problems on your own. Come back and check your answers. Now, let's write our givens. That might help you here. Okay, so right now we've been given some information about helium and oxygen, the two gases that they're going to add to the scuba tank. And if we are asked in this problem to get the partial pressure of each gas and eventually the total pressure of each gas, and really quick, if we come back up here, you're going to realize that we need to determine the moles of each gas that we are going to be using. So scroll back down, go back to exercise 25. And you can see that for helium and oxygen, we don't have moles indicated here, but we could easily use the ideal gas law, or Pivnert, to determine the moles of helium and the moles of oxygen. So essentially in the first step here, that's what you're going to do. So step 1, you are going to use N equals PVRT to determine the moles of helium and the moles of oxygen. So why don't you pause me, plug in those variables and calculate them and come back and we'll do the next step. Welcome back. You should have gotten 1.88 moles of helium and 0.49 moles of oxygen. And really quick, if you were to add up the moles, total moles of both, you would simply say N total would equal the moles of helium and the moles of oxygen, at which point, if you added 1.88 and 0.49, you should get 2.37 moles total of gas. Okay, so let's go to step 2. And here in step 2, we could actually use the ideal gas law, rearrange that equation to get the pressure of each gas. Remember, the helium gas and the oxygen gas in this particular example. So I can solve for pressure for helium. Let's go ahead and plug in these values. 1.9 moles, we just calculated from the previous step, times our R constant, our temperature in Kelvin, which is 298. And here you're going to divide it by the total volume of the tank that these gases are being held in. And if you go back to the problem, that was 5 liters. When I get the value here, I get the pressure exerted by helium is 9.3 atmospheres. And again, we could do the same thing for oxygen. So I'm going to go ahead and plug in these variables into the same equation, but this time for oxygen. Okay, so there you have the pressure exerted by helium and oxygen. We used the ideal gas law. We rearranged it to solve for pressure. Is another way you can do this problem, but I am doing it the most straightforward way. Lastly, we need to answer the question. And the question is, what is the total pressure in the tank? Well, we learned in the previous step, if you scroll back up, that the total pressure is the sum of all pressures in that particular scenario, and in this case, on our scuba tank. I'm going to scroll over here, you guys. We're kind of running off the paper. I apologize. So in step 3, the last step, you can say the total pressure is therefore the pressure of helium and oxygen. And when you add those two together, 9.3 atmospheres plus 2.4 atmospheres, your total pressure should therefore be 11.7 atmospheres. Exercise 26 is also another Dalton's law practice problem here, and it is saying the partial pressure of oxygen is observed to be 156 torr in the air, with a total atmospheric pressure of 743 torr. Calculate the mole fraction of O2 present. Again, I'm always going to encourage that you pull out the information that was given to you in the problem. There we have it. And it looks like if we go back to the previous page where there were several equations, we had talked about the pressure exerted by a specific gas, in this case oxygen, is going to be equal to the mole fraction of oxygen times the total pressure of the system, in this case the atmospheric pressure. Now, since we are asked to solve for mole fraction of oxygen, and we have been in fact given everything else, we'll simply rearrange the equation to solve for mole fraction. So divide both sides by P total. And therefore, if I rewrite the equation, the mole fraction of oxygen is equal to the pressure of oxygen divided by the total pressure. And again, the pressure of oxygen was 156 torr divided by 743 torr. Notice the torr cancels, and mole fraction is unitless. No units on mole fraction, okay? All right, let's do one more practice problem using Dalton's law, and that is saying the mole fraction of nitrogen in the air is 0.7808. Calculate the partial pressure of nitrogen in the air when the atmospheric pressure is 760 torr. Again, pull out your knowns. Mole fraction is 0.7808. The partial pressure of nitrogen is unknown. We're solving for that, and we're given the total pressure in the atmosphere. At this point, it's 760 torr. Again, go back to the equations on the previous page, and you will see that the partial pressure of nitrogen is equal to the mole fraction of nitrogen times the total pressure. You've been given everything but what we're solving for here in this case, and that's the partial pressure of nitrogen. So that is equal to 0.7808 times the total pressure of 760 torr. And when I multiply these two together, I in fact get 593 torr is the partial pressure exerted by nitrogen. All right. Now, before we end this podcast, we need to mention really quick the difference between a real gas versus an ideal gas. And at this point, we have been talking about ideal gases, which really, in essence, are just hypothetical gases. And truth be told, ideal gas law and all the things we've been learning about with the ideal gases, it really only can actually apply when those said gases are at low pressures and high temperatures. So before we end, I want you to scroll down to the top of page 17 and take a look at the contrasting points between an ideal gas and a real gas. I'm not going to read these to you because you can read. We're also going to do an activity that kind of helps solidify this. So if you are still having questions about the difference between an ideal gas and a real gas, hang tight. We're going to do some more practice. All right, I'm going to end the video right now. Thank you so much for watching.